So yes, I'm Curtis. I'm a professor at the University of Waterloo. And today I want to talk to you about one of my all-time favorite results in mathematics. This is the projective plane of order 10. And it's a computer-assisted proof, so I'll also be talking about work that I did in auditing that proof. How can we actually have confidence in what a computer tells us? So this problem has become known as Lamb's problem. How many people actually know about the projective plane of order 10? Anyone familiar with it? Okay, so this is a treat for me because now I get to describe to you this really beautiful math problem. And so I'm going to go over the history of it, and then I'll get to what I did at the end. Okay, so let's talk about what a projective plane is. Now, going to have a geometric structure here, right? We have points and lines, and it satisfies two very simple axioms. One is that every pair of lines are going to meet in exactly one unique point. The second is that for every pair of points, there's going to be exactly one unique line through those 2 points. Okay, now of course the Euclidean plane does not satisfy these axioms. It doesn't satisfy the first. You have parallel lines in the Euclidean plane. These are two lines that don't meet at all, let alone in a unique point. So the Euclidean plane doesn't satisfy this. However, this is now well known. You can construct the projective real plane by taking the Euclidean plane, projecting it onto the screen. And then if you have parallel lines that kind of go off to the infinity, go off to the horizon, well, actually, you can just add in the horizon now as a new line in your plane. And this is constructing the real projective plane. So now this is a model of those two axioms. Okay, so we do have, this is a consistent set of geometric axioms. Now I'm going to ask you a question which is maybe a bit strange, but it's similar to, once you know what the real numbers or the rational numbers, these are real fields that have infinitely many elements, you can ask the same question. Do finite projective planes exist, right? Do we have a finite set of points and lines which satisfies the axioms? Okay, yes. It's very simple, right? This is a trivial case, a triangle. You have the sides of the triangle, those are lines. If you consider the vertices of the triangle to be points, then yes, indeed. These two axioms are trivially satisfied. Now, can we come up with a non-trivial example? It turns out you can, and this is the simplest non-trivial example called the Fano plane. It was found by Gino Fano in 1892. He's kind of the founder of finite geometry. And yeah, it has 7 points, it has 7 lines, and you can convince yourself that all the axioms are satisfied. And if you're doing a double take about this purple circle, well, that purple circle is now a line, right? I say it's a line, so it's a line. It satisfies the axiom, so by definition, it's a line. And interestingly, I took a walk to the Museum of Science the other day here in Boston, and they have a little exhibit on projective geometry. And wouldn't you know it, you can see the Fano plane. Go to the Museum of Science. They have a nice mathematical exhibit. Anyway, so can we find anything more less trivial than that? This is the next largest case, and it's 13 points and 13 lines. One of the co-discoverers was Veblen in 1906. Okay, so these do exist, and to find the order of a plane, what you can do is we're going to classify the planes by the number of points on every line. It's going to be, if you have a projective plane of order 1, that means there's 2 points in every line. Projective plane of order 2, 3 points in every line. Projective plane of order 3, there's 4 points in every line. Okay, so, and we're denoted by ppn is for the projective plane of order n. Okay, so now here's the question. For what orders do projective planes exist? Now, it was classical from Veblen and Bussey in 1906 paper that they were able to construct projective planes in all prime power orders. Essentially, they use a very similar construction as the constructing the real projective plane, but use finite fields. And finite fields exist in all prime powers, and so you get projective planes in all prime power orders. Now, those aren't the only ones. So in the finite fields, right, there's only one finite field up to isomorphism for every prime power order. Interestingly, for projective planes, there's many more projective planes than just the ones you get from this construction. For example, Morehouse in 2010 can found over 309,000 projective planes of order 49. So there's tons of them. But what orders do they exist in? There's a famous conjecture, the prime power conjecture, that they only exist in prime power orders. This is still open. It's like the holy grail of finite geometry. every single projective plane anyone's ever constructed has a prime power order, right? They don't all come from finite fields, but they all have prime power orders as far as anyone knows. And I've talked with mathematicians who, are quite skeptical about this conjecture, right? They think, some of them believe it just because no one's found anything else, but it very well could be the case that they exist up for some non-prime power order. We do have a theorem of non-existence of Bruck and Reiser. This worked for some orders. If n is not the sum of two integer squares, and n is either 1 or 2 mod 4, then you cannot have a projective plane of order n. Okay, so it's a bit of a weird condition, but this rules out infinitely many cases. It doesn't rule out everything, though. Here is this state of affairs. So up to 9, everything's a prime power except for 6, and 6 is ruled out by the Bruck-Reiser theorem. Okay, so 6 is not the sum of two squares. And this brings me to 10, right? So 10 is the first non-trivial case. It is not ruled out by Bruck-Reiser because it is the sum of two squares. And of course, 10 is not a prime power. So which way is it? Does a PP10 exist or not? And this is what has become known as Lamb's problem. And this is, in theory, a completely finite search, right? It's definitely a solvable problem because there's only a finite number of possibilities to check, although, albeit an enormous possibility. You're never going to do this by just trial and error. Okay, there's 111 lines, 111 points. Every line would pass through exactly 11 points, right? So this thing would be enormous. And this is what, so it's named after Clement Lamb. It's an interesting history. He was a PhD student at Caltech in the early 1970s. His supervisor was Herbert Reiser of the Bruck-Reiser theorem. And so Lamb is choosing a thesis topic. He goes to Reiser and asks, okay, I want to work on the projective plane of order 10. Reiser says, I think this problem is too difficult. I don't think you might not get anywhere with it because this is a notoriously difficult problem. So what do you think Lamb does? Right? Now that we know the history, it's named after him, but he actually chose a different problem. Right? He didn't work on Lamb's problem. He took his supervisor's advice. And for the students in the audience, the moral of the story is you should probably listen to your advisor when they say a problem's too difficult, right? And he came back to it. So he became a professor at Concordia, which is in Montreal, and he started working on this problem 10 years later. So I want to just recount how the solution goes. We're going to do a simple translation from a projective plane to a 0-1 matrix. This is just capturing the set of incidences, right? So which points lie in which lines. You just fix an ordering of the points, fix an ordering of the lines, and then this is going to be a well-defined 0-1 matrix. So here's the first 3 projective planes in the 0-1 form. And what you can notice is going to be a quad-free matrix, right? There's not going to be any rectangles with 1s in the corners. Because if you had a rectangle with 1s in the corners, that would correspond to 2 lines that meet twice, right? You cannot have 2 lines meeting twice because every 2 lines meet once. That's the definition of a projective plane. Okay, so these are 0-1 matrices that are going to be equivalent to a projective plane. And here's a really interesting part. Right? Now that we have a 0-1 matrix, we can do linear algebra on it. Right? We're going to take the row space of the matrix, and not the row space over the reals, the row space over the simplest finite field, G of 2. Right? Just 0 or 1. So you're taking the sum of all the rows, linear combinations of the rows, modulo 2, and this is then just going to be a vector space of 0-1 vectors. Okay, this idea of looking at codes, right? We're going to call this vector space the code of the projective plane. It was spearheaded by Edward Asmus at a famous talk at Oberwolfach, where it was kind of an exciting time because people had been trying to find whether or not the PP10 existed, for decades. And then here's this approach where he actually was able to prove a lot of properties about this code. We don't know if it exists, right? But you can actually prove properties about if it existed, what would it look like? For example, the dimension would have to be exactly 56, right? So he was able to prove this, that the vector space the row space would be dimension 56. You can actually prove more. You can actually do things looking at the weights of the code words. So the weight of the 0-1 vector is just going to be the number of 1s in the vector. And these are all 0-1 vectors, right? So it's just basically the row sum. Okay, so that's the weight. And what the weight distribution would be is the number of, you count how many vectors there are of a given weight in the code. Okay, so let Wi count how many vectors there are of weight I. And you're able to derive this really striking equation. I think it's kind of strange where it comes from, right? It's actually derived from McWilliams identity. This is a remarkable result in coding theory, proven by Jessie McWilliams, who's shown on the slide here, in an amazing turn of events. So she was working at Bell Labs, took a year off from Bell Labs, and she completed her PhD at Harvard in 1 year. And in the PhD was her McWilliams identity. Right, essentially it relates the weight distribution of a code to the dual code. Anyway, so you used McWilliams identity, out pops this remarkable equation. It tells you exactly how many vectors there are of weight 19 in this code of PP10. It's in terms of the number of vectors of weights 12, 15, and 16. Okay, so this is where LAM starts. We're going to use this as our starting point. And Lam enters the picture. So now he's a professor in the 1980s. And up till now, everything was basically by hand. We're essentially reached the limits of human analysis, right? At this point, Lam he gets a team of programmers together, some of them shown here, and they're going to do a computer search, right? First of all, they make the assumption, let's say there's going to be a vector of weight 12 in the code. So W12 is positive. From that assumption, they create what I call a nightmare Sudoku. Right? So imagine you have a Sudoku book, right? The very last page is the final boss of Sudokus. You have to fill in this matrix. It's not exactly a Sudoku, right? It's a large matrix. You're filling in all of the blank entries, notice gray ones, and with either 0 or 1. Okay? You have to make, and the rule is you have to make every row have exactly 11 ones, and you can't have any quads in the matrix. No rectangles with ones in the corners. What you're doing is you're filling in the incidence matrix of the projected plane of order 10. And it would actually be even larger. It would actually be a square matrix, but this is kind of the most important part. And you can actually start to do this, right? You can actually start to fill in some of the entries with ones and zeros and actually get somewhere. But it seems like inevitably, you always run into a contradiction, right? And if you play Sudoku, you probably have this phenomenon. And if you really hate someone, you can give them a book of Sudokus. None of the Sudokus have solutions. Which is what happens here, right? And the thing is, it's very hard to find a Sudoku to prove it has no solution. You basically have to try every possibility. And it's like you can get very close to the very end, right? And it's like, okay, I have to backtrack. Oh, I get really close. This is what happens here, right? So they took a computer and they actually were able to show that Sudoku had no solution. It took the better part of a year. And this is the computer that they actually used. Now, this is back in the 80s. So computers were a lot larger back in the 80s. And if you're looking at this thing, which is on the table, that's not actually the computer. The computer's behind it in these big cabinets here. Right? So you thought this thing was large enough. No, it's the computer's in the cabinets behind it. Right? So they were much larger, they're much slower. But it worked, right? At the end of the day, they were able to show that the Sudoku had no solution, which is then going to be a proof that there are no vectors of weight 12 in the code. Okay, so it's basically a computer-assisted result that W12 is 0 if you trust what the computer tells you. Okay, and so similarly, you can do something similar with the weights 15, 16, and 19. And this was done in the 1970s and 80s. At the end, the very hardest case was showing the weight 19 was 0. It was done, it was not done on the computer we showed before, but this Cray supercomputer. So it's this imposing looking pillar where the computations take place in the center here. There's also a nice bench around it where you can sit and, well, as the computations are happening. So the bench apparently housed the cooling supplies and the power supplies. But yeah, that was the computer. It's about 100 to 1,000 times faster than Mac's machine, right? So I think it was essentially on par with like a 1 gigahertz Pentium, which is what I heard. So it's like, you know, not as fast as the computers today, but you know, it was very fast for the time. Okay, so the word started getting out, right? Once Lam's teams finished the search, and so they actually made the New York Times, they made Science Magazine. The paper was published in 1989, so this is before the work actually went through peer review. But you know, word had gotten around in the combinatorial community that they had disproved this, the PP10. It did not exist, right? At least if you trust what the computer told you, which now brings a kind of philosophical point, right? This was one of the first big computer assisted results, like the four-color theorem, which was in the 70s. Now in the 80s, we had the non-existence of the projective plane of order 10. And so Lamb did not consider it a mathematical proof. He said this is an experimental result because you have to trust the computer ran properly. And you also have to trust that it was programmed properly, which is, computers are pretty reliable. They will make, there are hardware errors, but there are almost certainly programmer errors. This is particularly the case when you're writing highly optimized code, right? So I've done a lot of programming in my time, and it's, you'll make bugs in even the simplest piece of software, especially when you start to write really highly optimized code, almost a guarantee you're going to have some kind of bug in the code. And so that's just the reality, which is kind of unfortunate from a mathematical point of view, because how do we trust the computer, right? Because there's almost certainly a bug. And this is actually exactly what happened. So there was an independent double check performed in 2011. And yeah, they did find discrepancies in Lamb's reported results. So they had missed some cases, right? So the proof is probably 99% correct, but there were cases which their code had overlooked. Okay, this is where I entered the picture. And what I did was maybe a strange thing to, at least at first, it sounds like a strange thing. I reduced the problem to one in Boolean logic. Okay, so what I did is I constructed this enormous logic puzzle, which has a solution if and only if the projective plane of order 10 exists. Okay, so it's just a statement in Boolean logic, although it's an enormous statement. And what's the benefit of that? Well, there's actually two. One is that we don't have to write any search code. We use what's called a SAT solver. SAT solver is an already written piece of software which is designed to solve logic puzzles. Right? You just give it as large of a logic puzzle as you want, and it'll read it, and it'll either say, okay, here's the solution, or there's no solution. Or it'll just keep running because there's no guarantee that this is it's going to be solved in any feasible amount of time. But the surprising thing is that SAT solvers will actually solve a lot of mathematical problems much faster than we have any theoretical reason to believe. Okay, and actually, if you're interested in SAT, come up to Bernardo's talk, which will be Friday at 10:40. He's going to be talking about how to apply SAT to mathematical problems. He also has a very nice webpage, satformath.com, which has dozens of papers which use SAT solvers to solve problems in mathematics, especially discrete mathematics. Okay, now actually the real reason why I wanted to use a SAT solver was the second point here, which is it actually, when the SAT solver says there's no solution to this logic puzzle, you don't have to trust it. This is the difference with where Lamb's code says there's no projective plane of order 10. You just have to trust that it was programmed correctly and the computer ran correctly. The SAT solver, though, you don't have to trust. It actually provides you a log with all the deductions it made in order to derive a contradiction. Okay, so it's an actual legitimate proof log. Now, this is not a human readable proof. It's billions and billions of lines of just logic statements. Every logic statement follows from the previous logical statement. So it is a mathematical proof, but it's just one you wouldn't want to read. But you can write very simple software which will check every single line follows from the previous lines, right? This is well known. And so it's very simple software which can audit the proof, right? So this is kind of the advantage from my point of view of using a SAT solver for something like this. It's that you have more assurance that no cases were missed, because if you trust that the SAT formulation is correct and you trust that the proof verifier is correct, then you can have guarantee that the final result is correct. And there was inevitably discrepancies. Actually, not only with Lamb's original result, remember the double check? There was also discrepancies with double check. Here's one of the things which we found on the right here. This is a 51 column partial projective plane. It doesn't extend to a full projective plane, but if it did, right, this was missed by the previous search. So in fact, the previous search basically asserted this thing not to exist. Well, it actually does, right? And so they had skipped it in their the code had missed it. Okay, just almost out of time, but I just want to finish with another example of SAT solving, which is Ramsey theory, which is pretty familiar to many of you, most likely, right? So in Ramsey theory, you basically define a PQ graph to say it has no P mutually connected vertices and no Q mutually unconnected vertices. So essentially, like a 3-3 graph would be a pentagram. There's no cliques of size 3, and there's no independent sets of size 3. You take the complement of the graph, there's also no triangles. Okay, so this is a 3-3 graph, and what Ramsey proved famously now is that arbitrarily large PQ graphs don't exist, right? At some point, you take the graph large enough, PQ graphs will stop existing. So that means the question then is, at what point do they stop existing, right? And this is the hard thing to find. This is actually the largest 3-3 graph. And so the Ramsey number is essentially the point at which you can't find 3-3 graphs anymore, right? So it turns out R33 is 6 because the pentagram is the largest 3-3 graph. So the pentagram has 5 vertices, there's no 6 vertex 3-3 graphs. And so this is the notoriously difficult problem, right? R55 is still unknown, even though 5 is a very small number. Erdős had a famous anecdote that he thought, okay, R55 is probably computable by humanity if we put all the computations of all the computers of the world together. But then he said, if an advanced alien life form were to come and say, we're going to destroy you unless you compute R66, he said, we better just wage war on the aliens. We're not going to compute R66. Okay, there are a couple of Ramsey numbers which are known. So R38 is one of the ones which is known. So in 1972, there was a 3-8 graph of order 27 found. Now, once you have the graph, it's easy to check it's a 3-8 graph. So we know that if the R38 number must be larger than 27. 20 years later, it was actually shown to be 28, basically by proving there are no 3-8 graphs of order 27. So that was the cutoff point, right? This is actually the optimal largest graph, 3-8 graph. However, again, you have the same problem. The disproof relied on computer computations, and there was nothing to check. You just have to trust the computer. And so we did that. We also used the SAT solver for this, right? You give the SAT solver, there exists a 28 vertex 3 graph. It's a big logical statement. The SAT solver starts from that, makes a bunch of logical deductions, finishes with a contradiction, and then that's a proof that that graph doesn't exist, right? So then R38 is at most 28, right? And then, so the proof is auditable, and also the lower bound's also auditable because you have the graph explicitly. So that lower bound's easy to check. Okay, just to summarize, I want to stress that these are enormous proofs, right? So they're in the gigabytes, hundreds of gigabytes, and then into the terabytes. So 110 terabytes for Lamb's problem in a compressed form. It takes 4 years to check that proof.
Wow.
Yeah, and that's distributed among many. Well, so we have 1,000 processors working on it, so you can do it in a couple of days. But yeah, so 4 years in total of CPU time. And just want to stress that no search code is trusted here. The thing that you are trusting, however, is the SAT encoding, right? So the logical puzzle that we formulated, that is taken on faith. But after that, basically everything after that is very well trusted. So there actually has been work that some people have worked on proving SAT formulations correct in a theorem prover like Lean. That hasn't been done for these problems, but we're hoping that it will be done in the future. So we'll have a complete end-to-end proof of Lamb's problem. All right, thank you all for your time.